See, we in the previous class we have just done with the colligative properties. We have discussed some questions also, right? So you will get the recordings and just please go through all the recordings. Yeah. And if there is any doubt, just ask me in your class. Okay, so basically there are four colligative properties, and just you should know what is colligative properties first, right? So colligative properties are basically those properties of solution that solely depends on the solute particles. Okay, that solely depends on the number of solute particles. So that's the colligative property. Okay, so we have done with the relative lowering of vapor pressure and elevation in boiling point. Okay, now today's topic is depression in freezing point. So depression in freezing point. Just write down the heading first. Yeah. So first let's see what is freezing point first. Freezing point. So do you know what is freezing point? Anyone? Can you tell me? Aniba and Jubita,
Yes, ma'am.
what is freezing point? Can you please explain?
It's like the temperature at which the liquid can turn into solid.
Yeah. So basically, freezing point is a point, or you can say temperature, right, at which the vapor pressure, right, vapor pressure of liquid phase is equal to the vapor pressure in solid phase, right? When the vapor pressure in the liquid phase it becomes equal to the vapor pressure in solid phase, then you can say that it is a freezing point. That temperature is known as a freezing point. Okay. Okay. So just write it down. What is freezing point? So it's the temperature at which vapor pressure of its liquid phase becomes equal, yeah, is equal with vapor pressure in the solid phase, right? So basically, vapor pressure it becomes equal to the vapor pressure of in solid phase. Okay. And now see, so it's a depression in freezing point, and we know that it's a colligative properties. So it must depends on the number of solute particles, right? So depression in freezing point means means that when you add, right, when you add your solute particles into the solvent, right? So the it depends. Basically, first write it down. See, just a second. See, suppose I'm just drawing the diagram. This is a container, right? It contains solvent particles. So, solvent, right? When you add non-volatile solute, right? We are talking about non-volatile solute, right? So when you add non-volatile solute into the solvent, so it will form solution, right? And this solution will contain the particles, your non-volatile solute, as well as your solvent, right? I'm just denoting this red color as a solvent particles, and by using this blue color, this is a non-volatile solute particles, right? So when a non-volatile solute is added to the solvent, the freezing point of the solution is always lower than that of pure solvent. See, this is the pure solvent, right? So this is the freezing point of the pure solvent, TF naught. TF naught is what? The freezing point of the pure solvent. And when we add the non-volatile solute, so what will happen? The freezing point of the solution, this solution, right? So the freezing point of the solution, it becomes lower, right? Freezing point becomes depressed, right? Reduced when you add the non-volatile solute. It becomes TF, right? So what is TF? TF is the freezing point of the solution. And this freezing point of the solution is always lower than that of the pure solvent, right? TF is lower than that of TF naught. When you add the non-volatile solute, right? So this non-volatile solute, it will reduce the your freezing point of the freezing point of the overall solution, right? And your TF is always less than TF naught in the case of non-volatile solute. Clear? Got it?
Yes, ma'am.
Yeah. So that's why, because it just depends on the solute particles, right? Because you can see over here, when you add the non-volatile solute, the freezing point, it reduces, right? It decreases. That's why it is known as depression in freezing point. Depression in freezing point, and it's solely dependent on the solute particles. That's why it is colligative property. Okay, so that's why it is colligative property. Yeah. So you just write it down. A solution will freeze will freeze when its vapor pressure become equal to vapor pressure of solid solvent. Solid solvent. Yeah, and now this in this case, you can see that vapor pressure of your liquid phase, right? This becomes equals to the solid phase. Vapor pressure of your liquid. This here vapor pressure of the solvent is equals to the vapor pressure of your solution, right? So in this case, the solution will freeze, right? Because its vapor pressure, it becomes equal to the vapor pressure of the solid solvent. Okay, so hence you can see that this this solution, it will start to freeze. Okay, and according to Raoult's law, according to Raoult's law, right? So when our non-volatile solid is added to the solvent, right? So its vapor pressure will decrease, right? And it become equal to that of the solid solvent at lower temperature. That's why this temperature is known as your depression in freezing point. Okay, and thus the freezing point of solvent decreases. Because according to Raoult's law, what we know, when any non-volatile, you can look into the picture, when a non-volatile solid, or you can write solute, is added to the solvent, what will happen? Solvent. So what will happen? Its vapor pressure decreases. Vapor pressure decreases, and it become equal to That of solid solvent. Solid. You can write solution equal to the solid phase. Right? Means the vapor pressure decreases and it becomes equal to the solid phase. Right? At lower temperature. At lower temperature. And thus freezing, thus freezing point of solvent solvent decreases. Okay, that's why the freezing point of solvent is less than that of your solution, right? Because vapor pressure also decreases and it becomes equal to the solid phase. Solid particles, the solid non-volatile particles. When the non-volatile solid particles or solid particles is being added to the solvent, its vapor pressure decreases, right? And it becomes equal to the solid phase, right? At lower temperature. Clear, Muniba and Jubita?
Yes, ma'am.
Yes, sir.
Yeah. So TF naught is always greater than TF. Temperature freezing point of pure solvent is always greater than the freezing point of solution. Okay, now see this graph. Let's understand this graph first. See this graph. This graph is basically a vapor pressure versus temperature graph, right? And this is a freezing point depression graph, right? So this graph is known as the freezing point depression graph or depression in freezing point graph. So let's see what it shows. So it shows how when we add a non-volatile solute to a pure solvent, what happens? So it lowers the freezing point of the solution when it is compared to the pure solvent. Okay, so we are talking about the pure solvent. When you add a non-volatile solute to a pure solvent, so what will happen? So the vapor pressure, it becomes equal to the vapor pressure of liquid phase it becomes equal to the vapor pressure of solid phase and it lowers the freezing point of the solution. Okay, so basically this graph typically plots between the temperature and vapor pressure, right? And basically it just shows that the freezing point of a solution is lower than that of the pure solvent, right? Means your TF naught is, you can say TF naught pure solvent freezing point is greater than TF, or you can also say the freezing point of solution is less than that of your pure solvent freezing point. Okay, so see first, you can see over here three curves. First one, which is in red color, this is liquid solvent curve. This is a solution curve, and this is a frozen solvent curve, right? Frozen after when you add the non-volatile solute to it to the pure solvent. So this is a graph after the addition, right? This frozen solvent. Okay. So see the pure solvent curve. So this represents the temperature, right? And vapor pressure relationship. We know very well vapor pressure versus temperature curve is there. So see the point where this curve interacts. See, this is a point where this curve interacts this with a solid phase, right? So this is the frozen solvent means this is the solid phase, black one, and this is a liquid phase, and this is a solution phase, right? So see this phase. So this is a liquid solvent phase means your pure प्योर सॉल्वेंट का जो फेज है, right? So pure solvent का जो curve है, so this red color, right? So the point where this curve interacts with the solid phase, see this solid phase, or the you can see the horizontal line over here, so it represents the solid's vapor pressure, right? That indicates the freezing point of the pure solvent, right? It indicates, see here, when you plot the perpendicular to it, right? So see, this is the freezing point of the pure solvent. See this TF naught. Okay. See, this is this blue color line. This blue color line, this is the solution curve, right? So this is the solution color, means solution contains solvent plus solute, right? So you can see over here, when you add the solute into the pure solvent, you can see the vapor pressure, or you can see the temperature freezing point, it decreases, right? The freezing point decreases. And now see, what is the freezing point? So see here, this line indicates this horizontal line, solid line, right? This intersection of the solid curve here, the intersection of the solid curve here with the solid phase line, right? See this horizontal line, right? So it indicates the freezing point of the solution, right? So when you draw the perpendicular to it, right? So this is TF. This is not TF not. Okay, so it's by mistake. So it's TF. It's only TF, right? TF. Okay, it means your freezing point of the solution. Freezing point of solution. यहाँ तक कोई problem, Muniba and Jubita? Clear? The two
Yes,
graphs,
ma'am.
liquid pure solvent ka graph and your pure solvent curve and your solution curve. Both is clear?
Yes, ma'am.
Yeah.
Yes.
Yeah. So the intersection here, this intersection, it just tells about the freezing point of the solution. Okay. And now see this, the difference between these two, the difference between the freezing point of your pure solvent and the solution freezing point is known as depression in freezing point, which is denoted by delta TF. Okay. So delta TF is what? So it's a depression in freezing point, which is the difference between this TF naught minus TF. What is delta TF? So delta TF is equals to your TF naught minus TF. The difference between the freezing point of the pure solvent minus your solution, right? So this is depression in freezing point. Clear? This graph is clear?
Yes, ma'am.
Yeah. Okay, now see. So depression in freezing point is also given by delta TF is equals to KF into M. Very important formula. Now what is KF? So KF here is where KF is molar depression constant. Molar depression constant. Okay, or sometimes it is also known as cryoscopic constant. Cryoscopic constant. Right? So basically, the depression in freezing point is the product of your molar depression constant and your molality. Right? What is M? Small m is your molality. Molality. Clear? And another formula is delta TF is equals to TF naught minus TF. And you know very well what is delta TF. So delta TF is your depression in freezing point. Depression in freezing point. And your TF naught is the, when it is not, it means it is, we are talking about the pure solvent, right? So the freezing point of pure solvent. And this TF is the freezing point of your solution. Okay, so basically, this graph is just it demonstrates that when you add a non-volatile solute to a solvent, the vapor pressure of the solvent it decreases, and it also lowers the temperature, right? So the temperature, the freezing point, you can say, it causes basically this lower vapor pressure means the solution needs to be cooled, right? This lower vapor pressure, what does it mean? So it means that solution needs to be cooled to a lower temperature, right? To achieve the same vapor pressure as a solid phase. Okay, that's why this caused the freezing point to be depressed. What is the reason of freezing point to be depressed? You can write it down. Yeah. just write this point also. I said that this lower vapor pressure means the solution needs to be cooled down to a lower temperature to achieve the same vapor pressure as the solid phase, right? So because we know that the vapor pressure of the liquid phase, it becomes equal to the vapor pressure of the solid phase. And for that, to achieve, to become equals to that vapor pressure of the solid phase, the temperature has to be lower, right? The temperature freezing point of the solution has to be depressed, right? Solid phase, which causing the freezing point to be depressed. Okay. And yeah, see, we know that delta TF means the depression in freezing point is equals to, and yeah, just remember the depression in freezing point is always directly proportional to concentration of solute, right? And also directly proportional to the molality. When the molality increases, the depression in freezing point also increases. Okay, so we know that delta TF is equals to KF, molar depression constant, into molality, right? So Kf into, what is the formula for molality? So the number of moles, right? So the molality is number of moles of solute divided by the mass of solvent in kg. That's the formula, right? And the number of moles we can write given mass, of solute upon your molecular mass of solute, right? And this into 1 upon given mass of solvent in kg. That's the formula, right? Formularity, right? So it's in kg, right? So when we have to just convert it into grams, so how to convert this? Just write kf into your W, weight of solute, upon molar mass of solute, into, it's in kg, right? So we have to just divide it by 1000 to get in gram solvent. Okay, and now we know that delta TF. What is delta TF? Depression in freezing point is equals to TF freezing point of pure solvent minus your freezing point of solution. Again, this formula came, very important formula, right? And see, what is the unit of KF? The units of KF, molar depression constant, is equals to, it's delta TF upon M, right? See here. So how to, delta TF is equals to KF into M. So from here, KF will be equals to delta TF upon your molality. And we know that what is delta TF? So it's a freezing point. It's basically a temperature, right? So temperature, its unit will be Kelvin, right? Kelvin upon, what is the unit of molality? So it's mole per kg, right? Mole per kg, right? So what will be the unit? So it will be mole, just I'm writing it over here. Just a second. Kelvin, it is first Kelvin, Kelvin per mole, and it's kg. Right. Or simply you can just write, that's the unit of kf your molar depletion constant. So what will be the unit? Kelvin per mole kg. Kelvin per mole kg. Clear, both of you?
Yes, ma'am.
Okay, so have you written each and everything? Now just write it from here. Just draw the graph, and just write down all the points. Yeah, this is TF, not TF not. It's only TF. Sometimes in the question they ask you to find the molecular mass of solute. Okay, so they will give you the value of depression constant, molar depression constant, and your depression in freezing point value, right? And your mass of your solute particles, and you have to just calculate the molecular mass, molar mass of that solute. Okay, so this last formula, say this last formula. So from here, this delta TF. See this formula. So from here, you can just derive the molecular formula for solute particles. It will be Kf into your weight of solute into 1000 upon your delta TF into your weight of solvent. This is in gram. That's why I have just divided it by 1000. Right. So this formula. Again, it's very important formula. Important formula. Okay, so whenever you just have to calculate the molecular mass of solute particles, and if the molar depression constant is given, delta TF value is given, right? So you just use this formula to calculate the molar mass. Clear? Now just right. Now you can continue. And just please write it down and please update me so that I will scroll down. Have you drawn the graph?
Yes, ma'am.
Okay. Okay. No writing.
Ma'am, can you please check the chat box?
Yes. Yeah.
Sorry, but can you check the chat box?
Just a second. Okay, Maniva, no problem. So please just go through the recordings, okay?
All right, ma'am. Thank you.
Okay, thank you. Yeah, Jivita, just write it down and please update me to scroll down. Written, Jivita?
Yes, ma'am. Done, ma'am.
And you know what? It has very day-to-day life applications also. Like, see, in the cold regions, like, so anti-freezing agents are added to the car radiators, right? Because car radiators will freeze out in that chilled climatic conditions, right? So anti-freezing agents are there with like your ethylene glycol. Ethylene glycol is an anti-freezing agent, right? So it is added to the car radiators to prevent the water, right? To prevent the water from freezing and so that it cannot harm the engine, especially in cold climatic conditions. Okay. And yeah, one more application is that road salting, right? So salt like sodium chloride is being spread on the roads, right, to melt the ice. To melt the ice. Why? Because it lowers the freezing point of water. The sodium chloride, it just lowers the freezing point of water and it causes the ice to melt at temperature below 0 degrees Celsius. Okay, so that's why the road salting we use in the cold regions.
Done.
Yeah.
Done.
It's just write on the last formula. And mark it as important formula.
Done.
Okay, so the next one is next qualitative property is your osmotic pressure, osmosis and osmotic pressure. Okay, so what is osmosis, Jyobita? Do you know what is osmosis?
The movement of solvent molecule from the lower concentration to higher concentration of a solution through semi-permeable membrane.
As the osmosis, right? So basically, osmotic pressure is also known as a colligative properties because it only depends on the concentration of solute particles, right, in a solution, not their identity. So that's why it is also a colligative property. Okay, and basically osmotic pressure, osmosis, and osmotic pressure is right. Yeah. So basically, is this osmotic pressure is the pressure which is required to prevent the flow of solvent molecules, right? This pressure is basically required. It is the extra pressure which is required to prevent the flow of solvent molecules across a semi-permeable membrane. Right, and this osmotic pressure is directly proportional to the molar concentration of solute. Okay, this is first. Let's write down the definition, then we will try to understand. Okay, so what is osmosis? So is the osmosis is the movement movement of solvent molecules from a region of, yeah, see, if I'm saying solvent की अगर मैं concentration ले रही हूँ तो I will write the region of high solvent concentration, because if the solvent is more, then absolutely it is known that solute will be in less amount. Means it will be a less concentrated solution, right? So osmosis is the movement of solvent molecules from a region of, you can add here, from a region of high solvent concentration, or you can to the region of low solvent concentration, right? Or you can also write osmosis is the movement of solvent molecules from a region of low solute concentration. Okay, if we are talking about the solute concentration, so the osmosis will be the low solute concentration to the high solute concentration. And if it is if it is for solvent, so osmosis is the movement of solvent molecules from a region of high solvent concentration to the region of low solvent concentration. Clear, Jovita?
Yes, ma'am.
Yeah. So just remember the difference. If I'm talking about the solute particles, so it will be higher solvent molecules or solvent concentration to the low, right? And if it is solute concentration, so it will be low to high. Okay, so I will write both the definition. Osmosis is the movement of solvent molecules from a region of high solvent concentration, or you can say lower solute concentration. Because when the solvent is high, right? If suppose if the solvent is more, like 100 ml, so it means that high solvent concentration means the solvent is more and the solute is less, right? So automatically it will be, whenever I say high solvent concentration, so automatically it means that lower solute concentration. Solute is less and solvent is more concentration. To a region lower solvent concentration. Concentration means here, or you can write or higher solute concentration. Right, and yeah, it will be across a semi-permeable membrane. Across a semi-permeable membrane. And what is semi-permeable membrane, Jovita? Semi-permeable membrane. Only selected particles can pass through it. Okay, semi-permeable. It will permit only selected members. Okay, means जिसके पास entry pass होगी, only they can pass through this membrane. Clear? Means only selected ones can pass through it. That means semi-permeable. Yeah.
Done, ma'am.
Okay. Now write down what is osmotic pressure. Osmotic pressure. So the pressure that must be applied to a solution to prevent the inflow, the inward flow of solvent molecules across a semi-permeable membrane. Right. So what is osmotic pressure? So basically, it's a pressure that must be applied to the solution in order to prevent the passage of solvent molecules into the solution, right? Which is through a semi-permeable membrane. Okay. So it is known as osmotic pressure. And basically, there are two types of semi-permeable membrane. Membranes are of two types, right? First is your natural. You can just write it down. Membranes जो होते हैं, they are of two types. Types होते हैं natural, right, and artificial, which is chemical based. Natural and chemical based. Natural may you can write vegetable membranes and animal membranes. Vegetable, vegetable membranes and animal membranes are used as a natural membrane. Yeah, so it can be in natural type of membrane. So it can be animal origin and plant origin. Like sometimes the animal membranes are made up of pig's bladder, right? They are made from the pig's bladder or parchment paper. Okay, so and this second one is your chemical based. So chemical based we just used as copper, ferrocyanide, ferrocyanide, right? Silicates of iron, silicates, iron, cobalt, and nickel. Silicates of iron, cobalt, and nickel. Right. So these are chemical or artificial type of membranes. Clear, Jyobita?
Yes, ma'am.
Another term is there, reverse osmosis. Okay, so what is reverse osmosis? So just opposite, right? When the when the pressure applied on the solution is greater than the osmotic pressure, right? So the solvent molecules starts flow from the solution into the solvent, right? Through a semi-permeable membrane, and this process is known as reverse osmosis. Okay, so just remember. Now see, we know that PV from the ideal gas equation, PV equals to nRT, right? This is from the ideal gas equation. Now P is what? It is pressure, right? So here in this case, pressure is osmotic pressure. So we can substitute the P as pi. And yeah, this osmotic pressure, it is denoted by pi. Osmotic pressure, it is denoted by pi, this, right? So we know that PV equals to nRT, right? From the ideal gas equation. So pi V, because it's a pressure, here pressure is your osmotic pressure, and osmotic pressure is denoted by pi. So pi V is equals to nRT here, right? So just write it down. What is pi? So pi is osmotic pressure, right? N is your number of moles, number of moles. R, you know very well what is R, so it's a gas constant. And yeah, T is your temperature, right? And V is what? V is volume. V is volume. Okay, now so PV equals to nRT, right? So from here, pi, which is osmotic pressure, will be equals to N upon V into RT, right? And what is N upon V? What is N upon V, Jupiter? Do you know? Number of moles per unit volume. Volume is denoted by what we call it as. It's molarity, right? It is molarity, right? So what is molarity? Molarity is the number of moles of solute per unit volume, right? Volume in liters, right? So it's a molarity. So can we substitute it here? Right, yeah, right. So we can write pi is equals to mRT, molarity into R into T, right? So from here, pi is equals to, what is molarity? Molarity is the concentration, right? It's a concentration, a way of finding concentration. So we can just write C instead of M, C into RT. So pi is equals to CRT. What is C? C is the concentration, right? Concentration of solution. R is your gas constant. T is your temperature. And your pi is your osmotic pressure. So that's the relationship between the osmotic pressure, your concentration, and your gas constant and temperature. Okay, so this formula is very important. Just write it down. Next here, pi is also equals to pi is equals to N upon V, right? Molarity is number of moles upon volume into your R into T, right? Now, what is number of moles? So, number of moles we can calculate by the given mass of solute upon your molar mass of solute into volume as it is into R into T. Okay. Now, from here, your molar mass of solute, you can calculate it using this formula. W of solute, weight of solute into R into T upon your osmotic pressure into volume. Okay, so that's the formula to calculate the molar mass of solute when the osmotic pressure is given. Okay, Jubita? Okay, now
Yes, ma'am.
you can write.
Done, ma'am. Done, ma'am.
Done. Okay. So now the colligative properties are completed. Okay, is there any doubt in any colligative property, Jovita?
No, ma'am.
Okay, so next topic is your abnormal molar mass. Okay, so what is abnormal molar mass? So basically, abnormal molar mass, it arises when the measured molar mass of a substance in a solution, it deviates from its expected value, right? What we expected, it doesn't give that value. It just deviates from that value due to the association and dissociation of solute particles. Okay, so due to association and dissociation of the solute particles, we didn't get as expected value. Okay, as we expected. So that is known as abnormal molecular mass. And this abnormal molecular mass, it arises due to the association and dissociation of your solute particles. Okay, solute molecules. Okay, so just write it down. Solute mass of a solute. Okay, substance in a solution deviates from its path. Expected value. Why? So due to association and association or dissociation. Association means combination, right? Dissociation means breakdown, right? So due to the when sometimes molecules combine and sometimes it just dissociate. So due to that, the abnormal molecular mass arise. Or dissociation of solute molecules. Okay, so basically this observed molecular mass is known as abnormal molecular mass. Okay, again I'm repeating, for any substances, right? For any substances, if it is undergoing association or dissociation, right? So, so in for if it is going on association or dissociation in the solution, right? So experimentally, the observed molecular mass, which is determined from the colligative properties, is different from the normal value, right? Normal value as we expected, right? So why it happens so due to the association and dissociation of the molecules in the solution. So this observed molecular mass is known as your abnormal molecular mass or abnormal molar mass. Okay, and this abnormal molar mass is basically a experimentally determined molar mass. Clear, Jibita?
Yes, ma'am.
Yeah. Now let's see what first case, association case. Association, right? So association means when solutes which undergo, for example, for let's say example, two molecules of solute, two molecules of solute after association, it forms a dimer. It forms a dimer. Okay. So basically, certain solutes where they undergo molecular association in the solution, right? And they form their aggregates. Okay, let's see. For example, if we take two molecules of benzoic acid, C6H5COOH, right? So so they will form dimers, right? When they will associate, right? Association will happen here. C6H5 COOH whole twice. So you can see here, after association, when these two molecules of solute, after association, they forms dimer. C6H5COOH whole twice. So it is forming a dimer. So it's a dimer of benzoic acid. Okay, so it's a 2 mole of benzoic acid. It forms dimer of benzoic acid after association. Okay, so these 2 moles are basically combining with each other, and they are forming the dimer. Okay, dimer of benzoic acid. So that's a case of association. Okay, so here you can see that the number of solute particles which is present in the solution, right? It is less than the number of particles which is expected to be present due to the association, right? See here, the number of solute particles which is present in the solution, right? It is less than the number of why? Because it just forms dimer. When it forms dimers, the number of solute particles which is present in the solution becomes less. It will be reduced due to the association. Second case, dissociation. Dissociation. Yeah. So certain electrolytic solutes, they undergo dissociation when dissolved in a solvent, right? So when the solutes gets dissolved in the solvent, it it undergoes dissociation, right? And there are two cases of dissociation. In case of a strong electrolyte solute, in the case of a strong electrolytic solutes, right? Let's see what will happen. First case. Second case, in the case of weak electrolytic solute. Weak electrolytic solutes. Okay, so let's see one by one. First one, in the case of a strong electrolytic solute, right? So the number of, see here, the number of particles of the solute in the solution is an exact multiple of the number of ions, right, which is present in 1 mole of solute. For example, let's take a strong electrolytic solute. For example, KCl in aqueous phase is just because it's a case of dissociation, right? So this KCl, it will dissociate to form K plus Cl minus ion, right? So 1 mole of KCl, right, it forms 1 mole of K plus ion and 1 mole of Cl minus ion. So you can see over here the number of particles of the solute in the solution is exact the multiple of the number of ions. Okay, it's just exact the multiple of the number of ions which is present in 1 mole of solute. Okay, so what we have just expected, we will not get the expected value of the molecular mass, right? So the molecular mass is just deviates, right? Deviates from the expected value due to the dissociation. You can see over here, right? So this is a case of dissociation. It's a case of a strong electrolytic solute, right? KCl is a strong electrolytic solute. Now see, if we take weak electrolytic solute, so in this case, for example, let's take example, weak electrolytic like your CH3COOH, right? Ethanoic acid. Plus, when you add water to it, right? So it will dissociate to form hydronium ion plus your CH3COO minus ion in aqueous phase, right? Another examples, ammonia. When you take ammonia and you will put some water in it, right? So it will dissociate to form this NH plus ion. Just a second. Plus ion plus OH minus ion, which is an aqueous phase. Okay, so you can see over here the number of particles of the solute in the solution phase. It is not an exact multiple of the number of ions, right? It is not the exact number of ions in the case of weak electrolytic solution, right? Because it depends the degree of dissociation. It just depends on the degree of dissociation. Okay, so just remember this. So in the strong electrolytic case, it will be the number of particles will be the exact multiple of the number of ions, right? And in the weak electrolytic solute, when we take weak electrolytic solute, so the number of particles of solute will not be equal to the, will not an exact multiple of the number of ions which is present in a 1 mole of solute particles. Okay, Jyobita?
Yes, ma'am.
Any doubt?
No, ma'am.
Okay. And yeah, this deviation, basically there is a factor which is Van 't Hoff factor, right? Van 't Hoff factor, this quantifies this deviation. Van 't Hoff factor quantifies this deviation, the abnormal molecular mass, the deviation. This when the solution deviates from its expected value due to association or dissociation, so there comes a factor which is known as Van 't Hoff factor. And that Van 't Hoff factor, it quantifies this deviation. right? So we will discuss further what is Wonder factor and what are the formulas. Okay, so first, just write it down. Have you written this?
Yes, ma'am.
Okay, now write this. Dissociation, both the cases of dissociation. Okay, so just remember how abnormal molecular mass rise. So it's due to the association and dissociation, right? And association, in association, what happens? Solute molecules, they combine to form larger molecules, larger aggregates, right? Which reduce the number of particles in the solution, right? And which increase the apparent molar mass, right? To increase the apparent molar mass. And what in the case of dissociation, as you can see here, so solute particles just break down, right, into a smaller ions or molecules, which increase the number of particles. When the number of particles is increasing, then there will be decrease in the apparent molar mass. Okay, in the case of dissociation, the apparent molar mass will decrease out, but in the case of association, it will increase. One topic is more, one to two topics are more, want of factor and how to calculate the degree of association or dissociation, right? So we will do this in the next class. And by the next class, in the next class, we will complete this chapter. Okay, Jupiter, we will complete this chapter and we will practice questions in that class. And if you have any doubt, so ask your doubt in the next class. Basically, we will practice more and more questions in that session. Because only one to two topics are left. They are very small topics.